Welcome back for the chapter 9.3 notes. We're still working with sets and probability, but now we're moving on to some applications of counting using our permutations and combinations. So it says many of our probability problems from chapter 8 can be solved using permutations and combinations. So let's look at example 1. It says, suppose 6 potential jurors remain in a jury pool and 2 are to be selected to sit on the jury for the trial. The races of the 6 potential jurors are 1 Hispanic, there are 3 Caucasian, 2 that are African American. If we select 1 juror at a time from the probability that on Caucasian and find the probability that 1 Caucasian and 1 African American are drawn. Okay, so we want to choose 2 people. And those 2 people, one has to be Caucasian and one has to be African American. So how do I choose the Caucasian? Well, there's 3 Caucasians to choose from. And order does not matter, and I want to choose one of them. And because they both have to happen, because it's an and, I'm multiplying. And I have 2 African Americans to choose from, and I want to choose one of them. Okay, so that's choosing the people that I want. So the probability is going to be the number that are Caucasian and African American divided by the number total. So we're going to find this in Desmos, and then the total number of ways I can just choose 2 people from those 6 would be 6 choosing 2. So let's go over to Desmos so that we can check this out. So in Desmos, if you want to use combinations and permutations, you're going to go down to the menu and over to functions, and then scroll all the way down, and then there's the permutations and combinations, and we're using combination. So the NCR, we're going to put in 6, 2 to find all of our possibilities. So there's 15 possibilities. And then I'm going to copy that because I can use it over again. And whoopsie. There we go. So I'm choosing for the Caucasian, there were 3, and I'm choosing one of them. And then there were 2 African American, and I'm choosing one of them. So there's 6 ways that I can choose 1 Caucasian and 1 African American. So my fraction is going to be 6 divided by 15, or 0.4 is the probability, or 40%. So there's the work. 6 ways I can choose my specific people divided by the number of ways that I can choose any 2 people out of the 6. Okay. Example 2. That's From a baseball team of 15 players, 4 are to be selected to present a list of grievances to the coach. I don't think he's going to be happy about that. So, how many ways can this be done? So we're not picking particular people. So it's just going to be 15 choosing 4. And that would be 1,365. Then in B, it says, one of the players is Michael Branson. Find the probability that Branson will be among the 4 selected. So I've got one that's going to be Branson, and the other 3, any player. So if I know I want one to be Michael Branson, I have to figure out how I can get that. So that would be choosing 1, because there's only 1 of him and I'm choosing him. And means I'm multiplying. And then the others, I'm choosing 3 of the other players. Well, if one of them is Michael, that means I'm choosing out of 14 players, I'm choosing the other 3. And then that's going to be divided by anybody. So, which would be all the combinations that we found in A. So that'd be 15 choosing 4. So notice that when I'm coming up with my numerator, it's always what I'm choosing has to add up to be the total number I'm wanting to select. So 1 plus 3 is the 4 players that I'm selecting. And then what I'm choosing, 1 plus 14, has to add up to my total possibility of 15. So let's go to Desmos so you can see how this is done. So I have 1 choosing 1, and that's just 1, but I'm doing it anyway because I wanted to show you that we have that placeholder for Michael times 14 choosing 3. So there's 364 ways that I can choose the specific people that I want out of the 15 choosing 4, 1,365. So we have 364 divided by 1,365, and we get the probability is 0.267. So let's go back to our paper for a moment. And we're looking at the last one. Let's find the probability that Branson will not be selected. So this is the way that he is selected, 0.267. So we have the probability of Branson plus the probability of not Branson, right? The complement, they have to equal 1. So if Branson is 0.267, we can find out what the probability of not Branson is. And so that will just be 1 minus 0.267 or 0.733. So that's using the complement rule that we've been talking about. Let's look at example 3. We're fun. We're putting all these things together that we've been learning. So example 3 says, a manufacturing company performs a quality control analysis on the ceramic tile it produces. It produces the tile in batches of 24 pieces. In the quality control analysis, the company tests 3 pieces of tile per batch. Suppose a batch of 24 tiles has 4 defective tiles. What is the probability that exactly one of the 3 ceramic tiles is defective? So we're testing 3. So 1 defective and 2 not defective, because we're choosing 3. So 1 defective, it says there are, for the defective, there's 4 tiles that are defective. So I've got 4 to choose from, and I want to choose 1 that's defective. The and means I'm multiplying, and then the rest of them, so 20 minus 4, there's 20 to choose from, and I want to choose 2 that are not defective. And then I'm going to divide by everybody. What's the number of ways that I can just choose any 3 tiles out of the 24? So 24, choosing 3. So I won't be going to decimals for all of these pieces, but most of them, so that you can see how I'm typing them into decimals. So we are going to go there right now, so you can see that. So I'm just copying a previous one to make it easier on myself. And it was choosing 2, 20, choosing 2, and then it was 4, choosing 1. Okay. And then that would be 760 is our numerator, divided by 20, whoops. $24, choosing 3. 2024. So that is 760 divided by 2024, and our probability is 0.3755. Usually I say to go to 4 decimal places or 3, usually 4. Let's go back to our paper here. So this is what it looks like, 0.3755. Okay, so now it says, if at least one of the tiles is defective, the company will not ship the batch. What is the probability that the batch is not shipped? So we want to know at least one. The probability X is at least one defective. So that would entail, let's look at all the situations where at least one is defective out of the 3. So that means 1 defective, right? 2 defective, or 3 defective. Or we could use the idea of at least 1. So at least 1, notice the only one we're not including is the 0, right? So we could use the complement. So 1 minus the probability of no defectives out of 3 chosen will get us to the same thing, because it's the complement. So we can say 1 minus, and then the probability of no defectives would be all good pieces. So that would be the 20 that we have to choose from, and we want to choose 3 of them. Out of all of the possibilities of 24, choosing 3. So let's go to Desmos so we can see how this is typed in. So we're going to say 1 minus so we get 0.4368. And actually, I just skipped and we just did part C. So we could have found the individuals and added them, but instead we used the complement. And that's what I had you do in part C. I kind of forgot. I jumped to that because I always want to jump to the shortcut. So we could find the probability that 1 is defective, 2 is defective, or 3 is defective. So that would be like what we did up here, where we had exactly 1. So we could switch it around and do probability of 1 defective plus the probability of 2 defective plus the probability of 3 defective. We already know this is 0.3755 from part A. So let's look at this one in Desmos. So so if we're going to have 2 defective, that means that we have 4 choosing 2 and then we have 20 choosing 1 because only 1 is not defective. So that probability is 0.0593. And then if we want to find the probability that 3 are defective, that means that we're going to have 3 defective and 0 over here because they have to add to 3. So that's 0.0020. And if we add those 3 probabilities, these 3 probabilities, we can see that we get 0.4368. So when we only have 3 probabilities to find and then add them, it's not that big of a deal. But if we had 5 or 6 or more to find and we had to add them, it would be a lot more complicated. So using the complement is going to be the easiest thing to use when we have at least 1. So at least 1 of anything, you're going to use the complement that says 1 minus the probability of none of those things. We're going to get a chance to practice with here again. So the next example is playing 5-card draw poker. Now, not everybody grows up playing cards, but 5-card draw poker means we have 52 cards and you're being dealt 5 cards to each player. So there's a total of 52 choosing 5. combinations of cards. 2,598,960 combinations of 5 cards. Such hands possible. Find the probability of being dealt each of the given hands. So we want a heart flush hand. That means all 5 hearts. So there are 13 hearts in a deck. And we want all 5 of them to be hearts. So that means we have 13 choosing 5 out of the total possible, which is 2, 5, 9, 8, 9, 60. So that's 1,287 divided by 2,598,960. We'll find that probability here in a minute when we go to Desmos. B. B says a flush of any suit. So 5 cards all from one suit. So this was what it is for just hearts, but we could do, there's 4 different suits. So it could be 4 times 13 choosing 5, all out of the 2,598,960. So let's see what that is. Let's go to Desmos. Again, I'm just copying one to use. So we have the big number is 52, and then we have, for part A, it was 13 choosing 5. So the probability of getting a heart flush is 0.0005, very, very small. And then for part B, we said 4 times that. So that probability is slightly bigger, but still very small. 0.00198. Then part C says a full house of aces and 8s. So 3 aces and 2 8s is what makes a full house. Let's go back to our paper for a moment so we can look at that. So a full house of aces and 8s. So we have 3 aces and 2 8s. A full house is 3 of one kind and 2 of the other. We are going to say 3 8s. Well, there's 4 aces in a deck. And there are 4 8s in a deck. So our probability would be 4 choosing 3 times 4 choosing 2 all over the 2,598,960. So we'll go back and find that one in Desmos here in a moment. And let's set up D while we're at it. So D says any full house. So any full house means that we could have 13 different ways we could do that. Because we could have 13 ways we could pick one card, and then there's 12 other card numbers to pick for the second. So we could do 13 times the 4 choosing 3 for the first card that has 3 of them. And then multiplied by 12, because if we chose like the jacks to have 3 jacks, then there's only 12 other cards that we could choose 2 of. So then there would be 4 choosing 2 of this. What up the second one? All over the 2,598,960. So let's go to Desmos to look at that, how they're typed in. So we have four choosing 3. And then 4 choosing 2. So this one's basically 0. There's 1, 2, 3, 4, 5, 6, 5 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 9. And then the part D, we had a 13 out here and 12 out here. And so that's more likely 0.001. 4, 4. So all of these are considered unusual because you're going to find once we get to chapter 10, any probability less than 5% is considered an unusual probability. So these are all unusually likely to happen. But when when you're playing cards, when you're playing poker, you get drawn a 5-card hand. So this is just a probability of being dealt that 5-card hand, but you do get opportunities to put down cards and take new cards. So your probabilities will go up slightly. Okay, let's look at examples. Example 5 says, a cooler contains 8 different kinds of soda, among which 3 cans are Pepsi, Classic, Coke, and Sprite. What is the probability when picking at random of selecting the 3 cans in the particular order listed in the previous sentence? Okay, so order is important. And we want Pepsi, then Classic Coke, then Sprite. So picking any of them in order is going to be 8 picking 3 with permutations. And that comes out to be 336 in Desmos. So that is any permutation, because order matters, of these 3. So that's our denominator. And then we want the particular probability of getting Pepsi, Coke, and then Sprite. So there's only one way to do that. So 1 out of 336 is 0.003. Example 6 says, suppose a group of 5 people are in a room. Find the probability that at least 2 of the people have the same birthday. Okay. So same month, same day, there's 365 options. Same month, same day. So the exact same birthday, there's 365 unless you were born on leap year, then there would be 366. But we're going with the 365. So choosing 5 people, and the order has to be important. So they have to have the same birthday. So all the possibilities would be 365 to the 5th, because they all have to have that one same birthday. And then we want to choose it says find the probability that at least 2 of the people have the same birthday. So that would be one pair. Okay. So because it's at least 2, we can say it's the at least one rule. So we can do the probability that none of them have the same. So 1 minus the probability that no 2 have the same. So we have to use permutations here because the ordering matters of how you pick them. So we have no 2 having the same, it would just be 365 permutating 5 out of the 365 to the 5th. So let's show you how that would be typed into Desmos. So we're going to go to our menu into functions, and we haven't really used permutations that much in this lesson. So there's the P. So we have 365, and we're choosing 5 of them. And then we have 365 to the 5th. So the probability is 0.9729. Okay. Now the last problem, example 7, is similar to this example 6, except for it's about the 50 governors of the states in the United States. It says, see example 6 above, and find the probability that at least 2 of the 50 US governors have the same birthday. So instead of choosing 5 people, we're choosing 50, right? So our denominator is going to be 365 to the 50th. That would be all the possibilities. And then we're going to use the complement rule. Which is 1 minus. And you know what? Up here, it should have been 1 minus down here, not up here. Sorry. So this is just the probability of nobody having the same. So we have to do 1 minus 0.9729. I miswrote that. So 97% is a probability that no 2 people have the same birthday. And we wanted at least 2 people to have the same birthday out of 5. So that would be 1 minus that, which would be 0.0271. Sorry about that. Okay. I had my 1 in the wrong place. So 1 minus 365 to the 50th. And then finding at least 2 of the 50 that match means that we're going to do 1 minus the probability that none of the 50 match. So that would be 365 permutating 50 people. So let's go back to Desmos and correct that. So that should have been my answer there. And then this is there. So 0.9704. So because there's 50 to choose from, it's much more likely that at least two people will have the same birthday. And so that's going to go up. So catch me back if you have any questions.